Yeah. Inderbitzen, sorry. I get tongue-tied all the time.
It's all good.
So, when asked what her favorite mineral, gem, or perhaps pure element was, she actually couldn't really decide and decided to go with all of the metallic sulfides that exist, specifically copper-based sulfides, if I remember
Yeah, copper, iron, sulfides.
Yeah. We do, yes. So one reason why that's actually pretty important is because a lot of those copper sulfides are formed at thermal vents at the very bottom of the ocean, which is probably one of your most interesting stories that I've heard about today. She got into marine geology based off of a Scholastics news article which showed those thermal vents. And ever since then, she's just slowly gotten more and more interested in it. So I think that that's a pretty neat story, and you should honestly talk to her more about it. She also collects books and tries to read about a chapter every night, so quite a few probably in your lifetime.
Oh yeah, definitely.
So, yeah. And overall, she's described her job and occupation as almost like a jack of all trades because the Earth is dang complicated. There's a lot of chemicals, physical processes, you probably all know. So yeah, Dr. Katie Inderbitzen.
I'm kind of loud, so that kind of helps me. Thank you, Joel, for the excellent introduction. The earth science I like to think of as the unifying science because it encompasses biology, chemistry, physics. So all you physics people who like to think that you're the unifying science, we're going to have to throw hands. Okay? So what I'd like to talk to you guys about today is how do we explore the seafloor? How do we explore what's underneath the seafloor, which is probably something that you guys haven't even thought about before. But first up, if I were to say to you just the deep ocean, how many of you would be completely terrified? Raise your hands. Okay, quite a few. Okay. Well, hopefully I will be able to assuage you of that today, because the deep sea is one of the most fascinating and yet poorly understood places on the planet. Okay, and it's really important, and I hope you guys all get excited about it.
Yeah.
So who am I? If you have not had a chance to talk to me yet, I'm a scientist. This is me at 14 in Hawaii with the Jason Project. That was kind of my initiation into doing live science. But I basically spent the better half of the last 15 years doing research at sea and under the sea using a variety of different vehicles, which I will go into in a minute. And I've also spent a lot of time making awesome costumes. So I also consider myself an artist. And so it's been an interesting life so far. And I'm not even halfway there yet, so it's going to be real good. So what do we think about when we think about the ocean, right? So first up, I had to add this because Ryan House had that awesome meme slide. So I'm like, well, I got to put in an ocean meme slide because there's some good ones. And so, I know this is kind of old, but, come visit the ocean. We have, cute jello and, angry boys and, yeah. And of course we have great animated GIFs. I love you guys, but you're gonna have to knock it off because we got a lot to get through today. I love that you're excited though. I love your enthusiasm. Okay, so what do we think of when we think of the ocean? We think of stuff like this, right? Coral reefs, clear, beautiful water, snorkeling. Maybe it's warm water that we think of. Maybe for some of us, I grew up in New England. I think of cold water when I think of the ocean. I actually don't like swimming in warm water because it's like a bathtub and I'm not into it. So this is what we think of, but the majority of the ocean is not like this, okay? Light only penetrates a couple of 100 meters into the upper ocean, and most of the ocean is actually dark, okay? And so, you may have heard or seen in kind of recent news and popular culture and things like that, that we don't know a whole lot about the seafloor. Things like, how little do we know about the ocean floor? How do we make maps of the ocean floor? We know more about the backside of the moon, Mars, than we do about the ocean floor. Things like that. And there's truth in all of these things because, number one, the seafloor is huge. remember that the ocean covers, almost 70% of the planet, okay? And the ocean is very large, it's very deep, and it's dark, okay? And so, you might say, but Katie, oh, wait, I forgot about this picture. So, this is great, yeah. So, we've mapped the moon, 100%. We've mapped Mars, 100%. And we've mapped the ocean floor, 5%. So, you can see where our problem starts, okay? So, but you might say, Katie, this map exists. This is a map that has all of the mid-ocean ridges. It has all of the trenches. It has a whole bunch of seamounts on it. This looks pretty good. So yeah, okay, yeah, we mapped the ocean. Yeah, we're good. Let's go on and do something else. The problem with this picture, or this map, is resolution. Okay, so the way that this map was created was using a satellite. Okay, and the thing about satellites is normally when we try to map things with satellites, we send out an electromagnetic wave, right? Okay? Now the issue with that is electromagnetic waves do not go into water. Okay? So now you're thinking, okay, well then how did we make this map? The way we made this map is because conveniently, above the highs, there are these little mounds of water that form, and where there's a low point, there's actually a very, very small dip. It's not that you would actually see if you were floating in the ocean, but it's there. It has to do with gravity, which I won't go into. But you get these little mounds and these little dips, and the satellite has an algorithm built in that can calculate, or that can work with that, and figure out what the actual depth of the ocean is, more or less, in that area. However, okay, this is the big issue. The issue is resolution. Okay, the resolution, or the pixel size on this map, is 5 kilometers. Okay, so imagine a 5 kilometer by 5 kilometer pixel on your computer screen. Okay, so that means that anything that's smaller than 5 kilometers is not going to be visible on a map like this. So yeah, we can see these huge features, but if you have a really small seamount that's maybe a quarter of a kilometer wide, it's not going to be visible on this map. So that begs the question, how do we begin to map the deep sea floor in a usable way? Okay, I'll show you a case study example of this. Excuse me. So this was an outcrop that we wanted to go to off the coast of Costa Rica. It's called Dorado. Yay, Costa Rica, yeah. So it's about a day's sail off of Costa Rica. And this was the existing map when we went out for the first time. Okay, so it's kind of blobby, you can't really tell what's going on. And then we went out with a vehicle and mapped it. So it looks completely different, right? Yeah, it has the same general shape. I'll kind of flip back and forth between the two so you can see the difference. So basically we were able to go in, and this is sub-meter resolution. Okay, so this is less than 1 meter resolution. So pretty high resolution. That's really good. But this took a really long time to do. This took a couple of weeks, and you can see from the scale bars here that this area is maybe only a few kilometers by a few kilometers. And if that took us a couple of weeks to do, you can imagine that, mapping the entire seafloor at this resolution is going to be really, really complicated and take a really, really long time and a lot of manpower, right? Okay. So how would we do it if we were to do it this way? We would basically use sonar. Okay, unsurprisingly, sound travels quite well through water. And we go out and we would basically mow the lawn with a ship. So exactly like you mow your lawn at home, we drive back and forth and back and forth and back and forth over an area until we've got a good map. Now, again, unfortunately, that takes a really, really long time. Okay, even if we're doing it with sonar, because you can't go too fast or else you don't get very good data. And then if we were to do it, let's say, instead of with sonar, if instead we dangled a camera on a cable and towed it behind the ship, that would take even longer, because if you're going to see anything usable, you can't drive too fast or else you're just, it's just going to look like speed lines going across the bottom. So you won't see anything, and then what's the point in actually doing it if you're not actually seeing it? So, okay, so we're going to talk about some of the vehicles that we use to explore the deep sea. Okay, and we're going to go kind of in order from least to most human involvement. Okay, so the first up, we've got autonomous underwater vehicles. Okay, AUVs. So these are your robots. Okay, these are things that you program to have a mission, and then you put them over the side, and they swim off, and they do what they're supposed to do, and then they come back and you pick them up. Okay, So very little human involvement except for doing the programming and putting them over the side. Okay? And so this is probably the most well-known AUV right now. It's Sentry. It's owned by the Woods Hole Oceanographic Institution. It was involved in doing some of the surveys looking for the Malaysian airline, the lost plane. It's been involved in a lot of kind of missing stuff in the ocean kinds of projects. In the upper left-hand corner, that's another kind of AUV. That's a wave glider. It's owned by MBARI, Monterey Bay Aquarium Research Institute. And that's really neat because it can collect data simultaneously from the atmosphere and from the water. And so you're getting kind of that interface between the air and water as it glides along. And then the one on the bottom right is a large water sampler. It looks kind of like a missile. But you can program these to basically drive around, go to a certain depth, take a water sample, drive around to another depth, get another water sample, things like that. And so they do require a support ship, generally, or because they don't have infinite power, right? They have, a battery, more or less, so they do need to come home eventually and either give us their data or give us their samples. So there's some human involvement, but it's mostly at the front or the back end. Okay, so we go from little human involvement. Oh, and this is really cool. So there's totally a guy in the Sentry group whose job it is to make a face on the Sentry during every single cruise. So in this, the cruise on the left, Sentry was testing out a new tool that was basically looked like a stick coming out of the front of him, so it looked like he was jousting. So they made him into a knight. And then the right-hand picture is from one of my cruises, which was at Christmas time. So instead of Sentry, we had Sentry claws. Very cute. Yeah, so one of the programmers, part of his job, and actually when they interviewed him for the job, they said, "How are you with making faces out of duct tape?" And he said, "Excuse me?" And they were like, "Yeah." And then they explained that part of his job was going to be that he had to make faces on the vehicle. And he said, "Oh, that sounds really cool." So he's really nice. Okay, so what Sentry has been probably best known for, at least science-wise, other than let's go out and look for things that fell in the ocean that we can't find, is the Deepwater Horizon follow-up work. Okay, so remember in 2010, Deepwater Horizon, vented oil for many, many months. There's a big problem. There's a big oil slick at the surface. But the question in the scientific community was, is there a midwater plume? Okay, so yeah, they've done all this stuff at the surface and they've mapped that part of the plume, but is there anything that's kind of hovering, a few hundred meters down? And can we sense that in some way? Can we figure out where it's going, how it's traveling, how fast is it going, so that we can mitigate any issues that might come along with that? And so basically what we were able to do with Sentry is put a mass spectrometer on it, okay? And we said, we want you to sniff out this one chemical. And so we put it in the water, and it went and it sniffed out this chemical, and that's what all these little dots are. So they were able to map the midwater plume continuing along the edge of the continental shelf a much further distance than BP was trying to say that the surface oil slick had extended. And we said, no, we can sense it at this level, so, clearly you are not correct, sir. So that's one of the best scientific uses that is probably fairly commonly known, at least for Sentry. Okay, so we've got our robots, autonomous, they go do their own thing. What if we want to be a little bit more involved in the process? Okay, then we would use something called an ROV. Okay, these are remotely operated vehicles. Okay, so these are tethered to a ship. So basically, you can have a really long dive because you've got more or less an infinite power supply, right? So for the most part, these tend to be two-body systems. Okay, so let's think about a boat out in the ocean. Okay, it's going up and down, it's going side to side, might be really, really heavy waves. If you just put something connected to the ship in the water just by itself, it's going to be going all over the place, and you're not going to be really able to get any good video or do a lot of science. So what we do is, in between the ROV vehicle and the ship, we have what we call a drop weight or a clump weight vehicle that basically just hangs on a cable, but then our ROV is connected to that by a fiber optic cable. Okay. And so it can swim free and not be affected by any of the heave that the ship is experiencing, but the clump weight will experience the heave, but not the ROV, which is very convenient, and eventually we'd like to go to no tether at all between the clump weight and the ROV, and people are working on that, and I'll show you that a little bit later. So some of the ones that I've been able to use, Jason is probably fairly famous. It's also owned by Woods Hole. Kaiko on the far right, that's owned by Jamstack in Japan. I got very lucky to go on a research cruise in Japan and work with Kaiko. And then the one on the upper right is Hercules, which if you've ever watched Nautilus Live, or if you came to my Underwater Time with Katie seminar, you watched a little bit of Nautilus Live. It's at nautiluslive.org. It basically, they broadcast live seafloor exploration when they're in the water, which is most of the summer. So, okay. So they do require a support ship, and they're controlled from the surface via, a fiber optic cable. And I have a time lapse of how these basically get launched. Because it's a two-body system, it's a little bit more complicated to launch. So they wheel out the ROV, they keep it in a hangar, for most of the time, so it doesn't get battered by the sea. And the first thing they'll do is they'll lift Hercules, the vehicle here. That'll go over the side with a crane, and then it swings around to the stern of the ship. And then the clump weight in this case is called Argus. Argus gets lifted over the side, and then they both get lowered together to the seafloor. Now, it's kind of neat. Nautilus's clump weight vehicle, they have a dual duty for it. It's not just there to be a heave compensator. It also has extra lights on. So if they're exploring an area and they want to have a whole bunch of extra light, they can just turn on some of the lights on Argus and get really, really good video. Okay, so what's it like doing ROV work? So the really neat thing about working with an ROV, at least from a scientist perspective, is that lots of people can be involved at once. Okay, so these things are controlled from basically a couple of, those big containers that they put on container ships. Imagine two of those welded together, and that's basically a control van. Okay, so we have a wall of monitors on one side, and the pilot has to use all of the views from the different cameras on the ROV to create a 3D kind of point of view, like they are the ROV on the seafloor, and so they know that, okay, this is over here, this is over here. So they have a very difficult job because they're trying to create 3D from a bunch of 2D screens. But the other great thing about it is that, so they're all up in the front piloting, and there's like 10 scientists in the back, working on getting some data, or working on collecting a sample, or trying to decide what we're going to do next in the dive. So it's really collaborative in this way, whereas some other ways, which you'll see in a minute, are a little bit more limited in the personnel you can have that are involved in doing the actual science. And the other thing that's really great about these is, like I just mentioned, with the advent of excellent internet, okay, very fast internet and great satellites, okay, we can actually broadcast live ROV dives from the seafloor direct to you, okay, and it's called telepresence. And so I put a screenshot of the Nautilus Live webpage on there. NOAA Ocean Explorer also has a stream that does this on the Okeanos Explorer. Both of these places have Twitter accounts, so they will always tweet when they're going to have a dive, so you can just, kind of flip through their Twitter and say, oh, they're diving today. Oh, I don't have anything going on, I've got a second monitor, I'll just, put this over here and see what's going on the seafloor. It makes science really accessible to the public. And that's one of the issues that we've had doing deep sea work for so long, is that it was hard to bring people with us when we go to sea. Okay, we go out for, maybe a month, and we're basically cut off from everybody. Even more so than at camp, we don't have any connectivity at all. We have email, but like trying to load Facebook, that's not going to work. So we usually just send email, and that's about it. So we have no idea what's going on in the world while we're out there. So, okay. And now we go from ROVs, okay, so we've had the robots that we tell what to do, we've had the ROVs that we can control remotely, now we've got the ultimate human involvement vehicle, okay, human-occupied vehicles. So these are the submersibles, okay. And how many people think there's a lot of research submersibles? I'm just kind of curious. Like, does anybody think there's more than 5? Okay, maybe a couple. There's not. Okay, there's very, very few research submersibles in the world. The ones I can name off the top of my head are Alvin, the Mirs, which are owned by Russia. Jamstack has one called Shinkai, and then China now has one called the Xiaolong. And those are the 4 main ones that are in operation right now. There are a couple other ones that used to be operated by the Hawaii Undersea Research Lab, but we've had issues with funding, so we can't really use them anymore. So human-occupied vehicles, you know, this is a very iconic image, right? So William Beebe, okay, decided back in the day that a sphere is going to be the best shape that's going to distribute the intense pressure of the deep sea, okay? So they're like, well, we're going to build a metal sphere, and we're going to get lowered on a cable into the deep sea and see what happens. And minus the cable, that is essentially what we still do, okay? Just new technology. We don't just drop it. You'll see in a second. So the one that I have the most experience with is the Alvin, okay? So the Alvin submersible is owned by the Atoll Oceanographic Institution. Its support ship is the RV Atlantis. This is the, if you're a history buff at all, this is the submersible that explored the Titanic, okay, in 1986. It did not find it. They found it with a towed cable system. And if you want to like chat with me about that, we can chat about that too. So Alvin is great. We just went through a $25 million upgrade about maybe 5 or 6 years ago now. Its original depth capability was 4,500 meters. When we finished the upgrade, we weren't able to get all of it done. We need to fix the batteries. We will eventually be able to access up to 6,500 meters down below the surface of the ocean, okay? And that means we can access 90% of the seafloor, okay? And so that's really important because if you really want to understand something and you can't get there, it's really hard to study, right? So if we can't get there, how the heck are we going to figure it out? So we can get there with Alvin. Okay, so Alvin, as you see from the stats, it's pretty heavy. It's, about 7 meters long. What's the new weight? I think it's like metric tons, 20.4 metric tons, okay? So that's really heavy. And so a lot of that weight actually comes from the titanium personnel sphere. Okay, so the personnel sphere, it's titanium. It's got 5 windows in it now, which is awesome. We get a really good view. And the inner diameter of that personnel sphere is a little bit over 2 meters. Okay, so 6 feet. Okay, it's a little bit over 6 feet. So the best way I can describe a dive, and that's actually on the right, that's a picture of my very first dive in Alvin. So that's me on the left, my colleague Bob Meldrum in the middle, he's Canadian, and then actually, so the pilot on the right, that's actually my boyfriend. We met in the submersible. We didn't get together until many years later, but yeah. He took me on my first 4 dives in the submarine, so that's pretty cool. But the best way I can think of to describe diving in Alvin is, okay, you and 2 people you don't know go in a broom closet, okay, and you're there for 9 hours. And okay, at the end of the 9 hours, one of 2 things is going to happen. You're either going to hate each other, or you're going to be best friends, right? So, and that's basically what happens on a dive. And it's really important that we work together because, like you see, there's only 3 of us in there. There's 2 scientists, 1 pilot, and we've got 9 hours to get a whole bunch of work done, okay? And the vehicle is really expensive, so the day rate for Alvin is somewhere around $35,000 to $40,000 a day, okay? And then ship time is on top of that. So you don't want to waste your time while you're down there. You want to have a lot of stuff to do, and you want to get as much done as possible and be very efficient. Okay, so how do we launch Alvin? It's actually quite a complex procedure. This gives you a good idea of the scale. And if you look at the width of the rope that goes around the lifting tee, you get kind of an idea of just how heavy this is and the engineering that has to exist in this A-frame for it to lift this 20 metric ton sub off of the ship, put it in the water, and then when it comes back up at the end of the day, pick it up out of the water and put it back on the ship without the ship flipping over, right? It's pretty wild. Okay, and then I have a time lapse of us launching the vehicle. So most of the time, the vehicle is in a hangar, because it keeps it safe that way. Keeps it away from the elements. So we wheel it out on these little railroad tracks, and we hook it up with the big line, and then we put the weights on. The scientists climb up the stairs, they get inside, everything gets closed up, they get lifted over the side, they drive away from the ship, and descend, okay? And so you might be wondering, well, how do you descend in something with this? How does it even float? Okay, so we have we generally have a positive buoyancy on the vehicle, so if we had no weights on it whatsoever, it would float. Okay, and they engineer that, everything that goes on the vehicle gets weight. Okay, even the people. So like, you have to be somewhat comfortable with yourself to like go into the main lab and stand on a scale and have the chief pilot read off your weight so that they can figure out how much weight they need to add to the vehicle, which is a little embarrassing the first time. So we start off with positive buoyancy. We strap these basically scrap iron metal weights to the side. That makes us heavy, and that makes us sink when we flood our ballast tanks. Okay? And then when we want to come up at the end of the day, we just drop our weights. Okay. So the important thing, at least one of the most important things I think about using a submersible versus an ROV, and now that I've done both, I can say this, is kind of the 3D perspective. So if I'm using an ROV, I'm just looking at screens. And really wherever we're looking at could be halfway across the world, and I wouldn't even know. But in the case of using a submersible, I can look out the window and immediately get a 3D idea of what's going on. And so when you're doing field geology, that's really important. And so some of the places that I've been with both an ROV and a submersible, I understand really well because I had seen it maybe with an ROV, but then I got to dive on it. And then I was able to say, oh, now this makes sense. I can put all of these images that I've had in my head into a 3D context. Because I don't immediately think like the pilots and create this 3D view. So it is really important to have eyes on the seafloor. Okay, now, why would you choose an ROV versus a submersible? Okay, and this is one of those times that you would choose an ROV. Okay, so Jason went out and they were going to be doing some exploring near an active undersea volcano, and they got there and it was erupting. And not just pillow lava, it was erupting quite violently. And as you can see, those little explosions. And so this is a case where you don't want people. Okay, you don't want people there. If this had happened and we were in the submersible, we would have left. Okay, and we wouldn't have been able to observe any of this because it's very, very dangerous. The windows actually on Alvin are just made out of plastic. It's a very special kind of plastic, but we always have to be very careful. There's temperature probes on either side of the window, so you always know what the window temperature is. So at one point, actually, in this video, and it doesn't show it, but Jason sat down into what was effectively a pool of elemental sulfur. And so the entire bottom of the ROV got coated in sulfur. And they were able to recover it, and it was fine, and they just scraped it all off. But if that had been a submersible, that would have been really, really, really bad, right? That could have been super dangerous, and people could have gotten hurt. And so that's one case, if we're going to be working in a dangerous situation, these are times when we'd actually want to use an ROV as opposed to a submersible. Also, ROV dives last a lot longer. Generally, Jason has a record 96-hour dive, okay? And so you're working around the clock. So you work for 4 hours on, and then you get 8 hours off, and then you work for another 4 hours, and you get 8 hours off. So it's great. So you can just keep doing science. And we can shuttle equipment up and down in the water column using things called elevators, so we can just keep working. Okay, so how do we access the subsea floor? Okay. So you've already seen that accessing the deep sea is pretty hard, right? It's not a cakewalk. So how do we actually get into the subsea floor and get into the rock? Okay, and so if you were in my directed study, this may be a little bit of a reminder, but don't completely tune out. We use scientific ocean drilling, okay? And this is not oil, okay? We are not allowed to go over there any hydrocarbons at all. But what we do is we can go out with one of these two drilling vessels. This is the JOIDES Resolution. The one on the right is the Chikyu, which is owned by Japan. The name means Earth, which is very fitting. And we're able to actually drill down through the sediment and get into the rock. And that's what we're really interested in. Okay. All right, so what I want to get into now is a little bit of a case study of how we use all of these different technologies together to kind of get at a problem or a big question that we have, a paradigm, if you will. So back in the 70s, there was this question of missing heat, okay? And so turns out when mid-ocean ridges spread apart, right, okay, they create new crust. The crust is hot, it cools, right? It cools as it ages. So turns out if you model that conductive cooling, that's this line right here, this dashed line, okay? But if we go out with a heat flow probe and try to measure the conductive heat that's actually coming out of the crust, we only measure these little red dots. And so the question was, well, where's that missing heat? It's not that it's missing, we just can't observe it. Turns out the missing heat is advective fluid flow or hydrothermal circulation. Okay, so cold water percolates into the rock, changes chemically, gets warm, and comes out again. Okay. Okay, I want to show you a little video of exactly what that looks like. So this is a 9-meter spire that is near the area that I worked on for my PhD. This was very unexpected. This area usually does not grow very tall chimneys, but you see the shimmering water. The shimmer is just a result of the differential in temperature. The bottom water temperature here is about 2 degrees C. This water is, should be around 270 to 280 degrees C. That's the reservoir temperature in this area. And so what happens is these mineral chimneys build up. There's all kinds of interesting structures that create them, or that are created in this process. And so this is where you get deposition of some of these things like metal sulfides. The first thing that actually precipitates out is what we call anhydrite. Okay, it's calcium sulfate. Okay, it's the non-hydrated crystal version. Okay. Okay, so that's enough of that. All right, so I would like to. We're going to pass around a rock. Okay, and this is basalt. Okay, so this is what most of the, well, all of the ocean crust is made out of, essentially, is this. And I don't know where this is from. I'm sorry, I did not collect this, so I can't tell you where it's from. It was just in my office when I started graduate school, and I kind of appropriated it. So when you get this, I'm going to pass it around. I want you to look at all of the holes, okay, all the holes that are inside. Okay. All right. So who can explain to me the difference between porosity and permeability? They're two very different things. Porosity and permeability. Anybody? Where?
Is porosity the amount of holes that the amount of holes that water can access in it?
Yeah, so basically, so that's right. So porosity is just the amount of holes, okay, in a rock or whatever you're talking about, a sediment. And then permeability is how connected those holes are, okay? So the pore space is the porosity, the permeability is how connected they are. Okay, so you can have a really holy rock. You know, you can have a permeable or a porous rock, and if they're not connected, if those holes aren't connected, it's not very permeable, right? Okay. So the upper layer of the ocean crust, which is that basalt that I'm passing around, is extremely porous, and that's the result of how it's erupted and formed at the seafloor. And so all those pore spaces allow for fluid to circulate around, right? Okay, we just saw hot water coming out of that in that last video. However, this circulation is one of the most poorly understood processes on the planet. Number one, because it's at the bottom of the ocean, and it's really difficult to actually see. Number two, because a lot of it is underneath the bottom of the ocean, and we really can't get in there. And number three, because we don't know anything about chemistry. Well, we know a little about chemistry, but we don't know extensively how long do these circulation cells persist? How large are they? Do they all look the same? Do they all run perpendicular or parallel to the ridge crest? We don't know. There are just a lot of questions that we have. So we really haven't begun to quantify this significant amount of circulation. And so why is this fluid flow important? Okay, so how many people have a cell phone? You all have cell phones, right? Okay, now, this is from Australia, but it still applies to us. So, the thing I want you to notice here is right here. More than 40 mined metals and rare earths are used to produce a single smartphone, okay? And some of the big ones that I want you to pay attention to are things like cobalt, okay? Cobalt, there's a significant amount in there's your 16 gigabyte iPhone 6. Okay, I know this is a little out of date, I'm sorry, like I couldn't find one for the newest iPhone. But you can look at this and you can see some of these metals that are used in here. You've got cobalt, you've got molybdenum, okay? Molybdenum is something that is really, like, we don't have a lot of molybdenum in the US, right? Okay? So when people say, and this goes for things about green technology as well, people say, oh, well, you know, we're going to do all this great stuff with green technology and batteries and everything. You got to think about this, because number one, we don't own a lot of the places that mine some of these things. Okay, rare earths are concentrated in hydrothermal systems. Okay, so there are people who are trying to develop deep sea mining right now. Okay, and so you can imagine the environmental impact that that could potentially have on an ecosystem that we do not understand. And so I always temper a little bit of caution when we just say, oh, well, we'll fix everything with green technology. We got to think about this too. We got to think about rare earths. We got to think about deep sea mining, because if saving the surface means completely destroying the seafloor, is it worth it? Okay. There's your little demo. Okay. So, turns out, this is very cool, so that porous rock that's still going around, turns out that if you set a whole big wedge of cold, wet sediment on top of that porous rock, you're not getting much water that's going to go through that, because sediment is very impermeable, okay? So the particles are small, they get very packed together, stacked on top of each other. You're not going to get a lot of water that comes through that vertically, okay? So the way that water actually starts to circulate around in the crust is these little nubs of rock that stick up above the sediment column, okay? And so some of them will start sucking water, okay? Some of them will start venting water. And I won't go into why that is, because it's kind of a long side story. But these circulation cells, the ones that we've actually been able to document, tend to run parallel to the ridge crest. Now, originally when they started doing this work, they thought, oh, well, it's going to be like, when you look at the convection cells in like an earth science book in the mantle, and they all run perpendicular to the ridge crest. That's not actually how it works, by the way. They thought that's exactly what was happening with the fluids as well. Turns out it's not. They do tend to run north-south instead of, or parallel to the ridge crest instead of perpendicular. So the sediment blanket basically isolates the porous part of the crust, and so this allows some of these circulation cells to exist for millions of years. We've found 20-million-year-old crust that still has evidence of fairly, recent hydrothermal circulation, and that was very surprising. And this is not very hot. This is maybe 40 to 60 degrees C. Okay, so it's warm, but it's not hot because it's moved away from the ridge crest. It's the crust has cooled. There's a lot less residual heat, but it's still flowing around. So it's warm, but not hot. Okay. So this is just another picture of that. That some of these will suck in water, some of them will blow out water. But then the question becomes, how do we try to see this? How do we observe this? Because we can look at the places where it goes in and where it comes out with things like heat flow probes and water chemistry, but we're interested in this. We want to know what happens here. So what we wanted to do was drill into the ocean crust, but then, if we're going to do that, we use 2 degrees C bottom water as our lubricant when we do scientific ocean drilling. So that's going to completely perturb the system, right? So we drill in, we inject all this, cold water. It's going to completely screw everything up. So the question in the community became, how can we observe this this phenomenon without disturbing it? And that's a thing you hear a lot in deep sea work, is how do we observe something without completely disturbing the natural system? Okay, so conveniently, as a result of people talking about this for a long time in the 80s, there was a workshop. Okay, so you will be invited to workshops, I'm sure. And at the end of one of the days of the workshop, they went to the bar, and basically this diagram got drawn on a napkin. They decided that, well, if we can drill a hole, we can put a cork in it. And so this is one of those instances of a backronym. Okay, so we had the acronym first, and then they had to back engineer what the words would be that would mean the thing that they wanted it to mean. So this ends up being a circulation obviation retrofit kit. And that's a lot of verbiage, right? Yeah, that's a lot. So break that down, circulation obviation, we basically wanted to stop any circulation that would be occurring between the bottom water and any water that was inside the crust. We're going to cut that off. And then and the retrofit kit part of it is the fact that we could go back to any hole that we had drilled, so long as it has a re-entry cone. Okay, we could go back to any of those holes and put one of these in. So it's a retrofit procedure. And that's basically what it is. It's just a giant metal cylinder that goes in, and we have some expandable inflatable packers that isolate the the rock, what we call the basement, from bottom water. We put it in, we let it come back to equilibrium, and then we can observe the natural system. And coming back to equilibrium takes a few years, so these are very, very long-term observatories. So what does it look like? This is our latest generation of corks. This is kind of the business end, the end that we work with on the seafloor. They're pretty tall. We assemble them below the rig floor on the drill ship. Okay, fun fact, I'm actually 8 years old. So this cork in particular was going in hole 1362A. So of course I wrote on it, stuck in the A-hole, because I'm actually 8 years old. And we paint all the corks because they start rusting almost instantaneously as soon as we put them on the seafloor. So we paint them, number one, to help protect them, and number two, so we can tell them apart, because they all start looking very, very similar. And in the area that we were working, we have 6 corks. So, we want to make sure we're at the right one before we start, playing with valves or anything like that. So we paint them. So where are these? Where is the system that we're working on? So the area we worked on is the Wandafuka Ridge flank, okay, which is about a day's sail off of Oregon and Washington. We usually go out of Astoria, if you've ever been there. That's where the Goonies house is. Pretty cool. So if we were to strip all of the sediment away from our map, here you can see our basement ridge. So this is the area that we thought that water was flowing. We thought water was flowing from south to north. And so any of the sites that say SR2, those are the sites we drilled in 2010. We had put some in initially in 2005, the year before I actually started working for my PhD advisor. This was, strangely enough, this was not even my PhD project. I just worked on it. So they had started putting them in, but getting one of these things to work is really complicated. Okay, so there's a lot of engineering that goes into it. There's a lot of moving parts that have to work just right. So the first couple of years of my PhD was us going out with Alvin and basically a 55-gallon drum of cement and trying to cement a couple of these corks that weren't sealed properly. Okay, so they were still sucking water in when they shouldn't have been. And we were trying to get them sealed up. It didn't work, but we tried. So they are engineering marvels in that. Okay. So what kind of data do we collect once we put one of these in and we got it working properly? So probably the most critical piece of data that we collect is pressure data. And we record that simultaneously at the seafloor and within the borehole. Okay. You're probably wondering, like, why would you measure pressure in the borehole? Wouldn't it just be the same as at the seafloor? Well, it turns out it's not. So interestingly enough, I like to use the analogy of the sponge. Okay, so even though the crust, that piece of rock that's going around that has all the holes in it, even though that's a rock, that is compressible. Okay, and so if you think about a dry sponge, it's got a lot of holes in it, it's porous, it's probably permeable, it doesn't look like you can squish it, but if you mash it together really, 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 really hard, you can compress it. Okay, and I'll pass this around so you guys can all try. So the crust is compressible, but how are we loading the crust? Okay, what's the thing that's providing the pressure that's pushing down on the crust? Okay, so we have a water column, right, that's sitting on top of this. Now, what kind of, let's say, a periodic, cyclic loading, what do you think that might, what kind of thing do you think that might be that would be pushing down on the crust and maybe lightening up on it and pushing down? Maybe something that happens on a day scale. Tides, exactly. So it turns out we have a 2-meter tide in this area, okay? So 2 meters, right? That's like almost a gallon, right? It's almost a gallon. It's not quite a gallon, but it's almost a gallon. So just imagine the change in the height of your water column that much over a day scale, okay? And so remember, the pressure in a column of liquid is rho GH, right? Okay? So that height is going to be changing the amount of pressure that we're pushing down onto the crust. Okay? And that's one way we can actually also help drive fluid flow. And so when they first started getting pressure measurements, they noticed that you could see the tide recorded in the borehole. And the only thing that's different about it is that the amplitude is decreased by how compressible the rock is. Okay, so you basically have a time, but it's slightly smaller amplitude. And I won't get into why, because that's a whole other long story, but it's pretty cool. But the thing is, about these things, we have to go physically plug into them in order to download our data. So this is, again, where ROVs and submersibles come in, because we have to physically go out and touch our data units. Okay, so this is a different court. This is the one I worked on for my PhD. The toilet brush is the most important thing that we bring on the expedition, because we have to clean off our data receivers. So we have to clean everything off. We want to make sure we're not pushing any sediment or microbes or anything into the ports, because that could cause an electrical short. It could, blow the whole system. It would be really bad. So we make sure that it's cleaned up really good, and then we get our data connector, and we're able to put it on. And then I'm sitting inside the submersible, and I have basically a computer that's connected to the cable, and I talk to the data logger, and I say, hey, wake up, give me your data. And then I have to download all the data, which at this site, because it's one of our older ones, only happens at 9600 baud. Okay, so that's real slow. So it usually takes a couple of hours to get a good chunk of data. The other neat thing about these is that most of the pressure case is battery. Okay, so the pressure case will probably be about that big, and most of this is battery. Okay, it's a cylinder. Because the way these work is that, we put them down there, they wake up every, once an hour or whatever it is we have them programmed for. They wake up, they take a sample, they go back to sleep. Okay? The actual data logger instrumentation part is 3 little cards that are like this big, okay? So like maybe half the size of an index card. And then you're never going to guess what we store the data on. Compact flash cards. Okay, so not even SD cards, compact flash cards. So the PI for the project basically went on eBay and bought up a couple people's lots of old compact flash cards so that we could keep making the data loggers. Because the programming we were using was so simplistic that it could handle dealing with an SD card. We'd like to change that moving forward, but for now it works. We're going to stick with what works. Okay. Okay, so what other kinds of data can we collect with a core? We can actually collect continuous fluid chemistry data. Okay, and these are really, really cool. These have 0 batteries. Okay, basically what we do, they're called osmo samplers. They use the pressure across the osmotic pressure across a membrane. That's how they work. We basically create a briny reservoir on one side of a membrane, and then we hook the fresh side up to a sample coil that's filled with DI, more or less. And as the fresh water wants to go over to the salty side, right, it draws in fluid into our sampling tube, okay? And so we know the rate that our pump pumps, we know the diameter of our tubing, and so we're able to figure out exactly how much, what length of tubing represents X amount of time. So we can say, all right, well, based on our pump rate and our tube diameter, 1 meter of tubing is equivalent to 1 day of sampling. Okay, so you can really get very fine scale chemistry sampling, and if you're trying to measure things that are changing over time, this is very useful because you could say, well, okay, this week it was, the chemistry was this week, but next week it was totally different. And so we could do this not only with like a Teflon tube, but we can also use a copper tube, like here, if we want to do dissolved gases, so carbon dioxide, methane, things like that, that might have been a result of microbial activity, things like that. Also, we can utilize these osmo samplers for microbiology. Okay? And if you're at all into microbiology, sub-sea floor microbiology is super duper hot right now. Okay? Like it's really, really hot. There's a lot of grant money. The people who funded my postdoc are microbiologists. Okay? So if you're interested in micro, there's a lot of, there's a lot of places you can go because we don't know almost nothing about sub-sea floor microbiology. So if that's your gig, you might want to look into that. But what we can do with osmo samplers is we can bathe samples of different kinds of rock, different minerals. We can bathe them with fluid from the borehole, and we can see what microbes grow there. Okay, how do they alter the different pieces of rock? And so they call them flocks, or flow-through osmo chamber samplers, I think is what they're called, where they can look and see what's colonizing the different kinds of minerals and the different kinds of rocks. It's very, very cool, and I've seen them come out of the borehole after they've been in there for like 6 years. That's the other thing. These things run for like 6 years on table salt. Okay? So that's basically all we do is we just buy like the big things of the iodized salt, and we fill this reservoir, and it'll run for 6 years. So this one hung in a borehole for, I think 6.5 years, and we got really, really good samples from it. So, okay, all right, so this is just to give you an idea of what one of these looks like on the seafloor, okay? So here's the fluid sampling bay. You can see one of those Osmo samplers hanging off the bottom there in a milk crate. I like to say that most deep sea science is done with hose clamps, zip ties, and duct tape. Okay, those are 3 very critical things that we do. In the case of this cork, we also actually were able to have a flow meter on one side. We were able to open a big ball valve and allow the formation to vent fluid for a year. And we were interested in looking at the pressure drawdown around the cork, and so that we could make some inferences about the physical properties of the crust. How porous is it? How permeable is it? Things like that. Those results are not available yet, but we are working on them. The other really cool thing that we did in 2010 as part of putting in these new corks was a tracer injection test. Okay, and so how many people know something about like groundwater well testing? Just a few of you. Okay. So imagine doing that same kind of procedure. And so those of you who don't know, you basically have one well where you might inject something, and then you've got all these other observation wells where you're going to be recording data from to see, oh, how long it takes to get from here to here, things like that. Imagine doing that at the bottom of the ocean. Okay, really, really complicated, and this is the first time that we did it in 2010. So basically what we did was we chose one of our new corks, 1362B, and we basically injected a whole bunch of things, and we were interested to see, does it go to the south? Does it indeed go to the north? We think flow is to the north, but does it actually go that way? Do we see any out here perpendicular? We didn't know what we were going to get. It was kind of cool. So we didn't get any press because 2010, what happened in 2010? Deepwater Horizon, okay? So the word drilling was a big no-no. And so none of the work that we did, even though we did really, really interesting engineering stuff, got talked about because everybody would hear drilling and then immediately go, oh no, it's oil, it's awful, which we weren't even doing anything with that. We were looking at rocks that don't have any oil, and there's no oil in the salt. So what did we inject? We injected SF6, which is sulfur hexafluoride, which is a non-reactive gas that's commonly used in hydrology. We also injected some rare earth salts so that those would get picked up in the fluid, and we'd be able to see those in our Osmo sampler when we recovered it. And then we also did at the end a 24-hour freshwater pulse. So we just pumped in fresh water for 24 hours. So that's a lot of fresh water. So what did that tell us about the effective porosity of the crust in this area? And you might be wondering, like, oh, well, couldn't you just measure this remotely? Like, why did you have to do it this way? Turns out if you try to measure porosity and permeability with a drill ship, you get a very localized signal, so just whatever is right around the hole that you've isolated. But if you want to get a regional signal, this is really the only way you can do it. So what did it tell us? And so here's our first paper on it, which was 2016. Okay, so think about this. First corks went in 2005. The drilling leg I was on, 2010. Then we went back in 2011, 2013, and 2014 with an ROV or Alvin to get data. Okay, so this is a long-term project. Okay, so when you write your grant, and these are not cheap. Each one of these corks costs $1 million to put in. Okay, they are a lot of money. This is a big grant to be asking NSF for, and it is a hard time at NSF right now, let me tell you. But when we finally started getting our results, and these are just from the sulfur hexafluoride, initially, so we pumped it in, and then initially there was a little bit of a backflow, which they were expecting for hydrological reasons, but over time, we saw a predominantly northward flow of the sulfur hexafluoride. And what we actually found out is that the speed of flow was about 2 to 3 meters a day. Okay, and this area had been numerically modeled before for like porosity, permeability, how fast would fluid move. And so when we got numbers like 2 to 3 meters a day, we were surprised because that was a lot higher than we had expected based on our numerical modeling. And what was also surprising was that our effective porosity was under 1%. That's not so far off from what we had measured. However, with how fast the fluid is actually flowing, that tells us that our crustal structure here is heterogeneous. Okay, so it's not all the same structure. You're actually seeing areas where you would get channelized flow. Okay, so areas where it's a lot more permeable, and maybe those areas are isolated from other areas. So we're still working on this. We haven't finished working with all of the data, and this wasn't even my PhD project. So I just helped out with this. But it was really neat because you kind of got to go all the way from, okay, here's a question we want to answer. Here's the engineering we had to develop in order to do, or to answer that question, or try to answer the question. And then here are some results, finally, after a good 10 years. Okay. Okay, now I'm gonna pull a shiver here. Everybody stand up, stretch. Stand up, stretch. Just for a hot second. Stretch. I know it's really warm in here. I know you got back from an overnighter. I know you're exhausted. You're gonna sleep really well tonight. Okay, all right, sit down. Okay, everybody has a stretch break. That's good. And Brian's stealing my things. Okay, okay. There's no need to talk. I love you all. Okay. So now here's the crux. So like I've talked a lot at you about vehicles and science. This is the reason I do this talk. Okay, why do we care about the seafloor? And specifically, why is studying the deep sea important? Because it's really, really, really important. And so, the first thing that comes to mind for me is this cartoon. This is a very famous cartoon. It was in the New Yorker, and it's these ladies who lunch, sitting around saying, I don't know why I don't care about the bottom of the ocean, but I don't. And that is a common thing that I have seen in society. Okay, the average person probably doesn't care about the bottom of the ocean, but they don't know why. Okay? So, why do you guys care? Remember those little things we did the other night? Those word associations? There was a purpose, okay? So, I know you all see your words and it's very exciting. Okay, we need to get through this. So, what are things that are important to you guys? Fish. Some of you gave me synonyms and maybe not nouns, and that's okay, I love you anyways, it's fine. So there are some really good ones here. So we've got squid, submarines, rocks, coral, fishermen. I got a number of aerials from like The Little Mermaid, and I was a little confused, but that's okay. That's okay if you associate that with the deep sea, that's fine. Anglerfish, hatchetfish, whales. Okay, these are all reasons that we should care about the ocean. Okay, even if they seem a little silly to you. Even if it is Ariel, the Little Mermaid. Like, these are reasons that we should care about the ocean. And then if you go to your adjectives, guys. So if you go to your adjectives, the biggest one, somebody told me I was going to have a sampling bias for blue. Look at dark, it's so much bigger. There were so many more darks than blues. We got a lot of deeps. Okay, so whoever took boring and depressing, I hope you feel differently now. This is why I didn't want you to put your names on those papers. So surprisingly, last year when I did this, I got a lot of wet. And so thank you for not giving me a lot of wet. That was very good. Difficult, I really appreciated difficult as an adjective. So hold till the end and I'll take all the questions, okay? And these two were a little confusing. I appreciate that you think the deep sea is sexy. I also think it's sexy, but probably for not the same reasons. And I don't know if it's dank, but whatever floats your boat, I suppose. Okay, so these are all things, these are all reasons to care about the deep sea, right? Okay. Now, okay, and we might need some volume on this, Brian. Okay. So, back in the day, everybody's heard JFK's moon speeches, right? He's very, we choose to go to the moon in this decade, all of that. Now, did you also know that JFK, had he lived, intended to create basically an ocean NASA? Okay? So listen to this quote. Oh, wait, hold on. Didn't do it. Hold on. Click.
Can you turn up your computer volume?
It's because we all came from the sea. And it is an interesting biological fact same percentage of salt in our blood that exists in the ocean. And therefore, we have salt in our blood, in our sweat, in our tears. We are tied to the ocean. And when we go back to the sea, whether it is to sail or to watch it, we are going back to whence we came.
Okay, now, if you recognize that, that's actually the opening of Sequest DSV, which was a really awesome show in the early 90s. And I loved it, and I was really sad when it suddenly went to aliens and got really bad, and definitely jumped the shark. But the first season was really good, and that's the opening from the pilot episode. And I remember being like 12 and being like, oh, we're tied to the sea. This is so cool. We have blood, we have salt in our blood, and our sweat, and our tears. So that's actually, JFK gave that speech to the America's Cup in the, I forget what year, but it was in Australia. And yeah, it's very poignant to me. Had he lived, we might have had an ocean NASA. Okay, so that's a little sad. But it's another reason we need to care about the ocean. Why else do we need to care about the ocean? Well, I'm sure you're going to, the big one, climate change, okay? So, as the ocean warms, okay, warm water cannot hold as much oxygen, okay? So, we're starting to see large areas that are going suboxic or anoxic, okay? And these basins are just off the coast. They're just off of LA and San Diego. I was out with the Nautilus a few years ago, and we explored a couple of these areas. And so, there's no oxygen. It makes it very difficult for anything to live. And so that's bad for fisheries, right? So if nothing can live there, your fish aren't going to want to live there, and that's bad for your local fisheries system. Going along with that, warm water also, in a lot of cases, tends to be quite acidic. Okay, so the ocean acts as a buffer between the atmosphere, or with the atmosphere. So when carbon dioxide hits the surface ocean, it forms carbonic acid. And if you have too much carbonic acid, you're going to be dissolving your oyster shells. You're going to be dissolving anything that uses calcium carbonate to make its house, okay? And so we actually see that in farmed oysters, and I have a colleague who works with oyster farmers to basically use seagrass to bring down their local acidification problems so that their oysters can actually still create a shell. I mentioned this before, to mine or not to mine, okay? Mining the seafloor, this is a thing, okay? There's actually part of the UN is called the International Seabed Authority, and some of you who were in the economics DS last block might have talked about this a little bit, but the International Seabed Authority, they're the people who give out the mining permits, okay? And the interesting thing about that is that the United States did not ratify the UN's Law of the Sea Treaty. So we do not sit at the table on the ISBA. Okay, so we have no say. We are there at their pleasure right now. They invite some scientists because they know they need to have some scientists, and they know they need to do environmental impact studies and things like that. But we are there at their pleasure. So one of those things you need to think about. So batteries, anything that uses batteries, especially new high-tech things, cobalt, graphite, lithium, manganese, okay? Cobalt, manganese, molybdenum, these are found heavily in hydrothermal systems, okay? Also in manganese nodules. So these are things that precipitate out of the ocean naturally, just on their own, okay? And there's a bunch here, if you've heard the Clarion-Clipperton fracture zone area, there's quite a lot of these manganese nodules there. And so one of the things that people want to do is basically go out with a big vacuum and vacuum up all of these manganese nodules, which, conceptually doesn't sound that hard, right? But remember, you're in like a 4,500 meter water column, and then you're blowing up all of the silt, and you're basically practically destroying the entire environment around you. So is it worth it? Does the cost outweigh the gains? And so yeah, so we could find a lot of rare earths for smartphones and green technology, but are we completely destroying an environment that we know almost nothing about in the process? And so this is a dilemma that we're going through right now. And then also at kind of the base level pollution. Okay? I'm sure you guys have heard lots about microplastics. Okay? And so I wanted to share with you a couple of recent studies that came out. So there was a cruise off of Monterey in the canyon. And so a lot of people think that all the microplastics are at the surface. Well, that's not really true. So here's a plot of the microplastics, and you can see most of the microplastics are at several hundred meters down, okay? So these aren't things that we can just go out and scoop up off the surface, okay? And also these are like teeny little things, okay? So this then begs the question, how do we solve this? And, we look at, we need to do more work at outflow sites like river mouths, okay? There's a great group that does these trash wheels. There's one in Baltimore Harbor, it's called Mr. Trash Wheel. He has a Twitter. He's really cool, he's got googly eyes. But basically all the river water goes through the trash wheel and it filters out all of the trash that's in that, and then that can be carted away. And so a lot of people think that, oh, well, we need to go to the great, Pacific garbage patch, which, spoiler alert, does not look like a garbage patch, it just looks like ocean. There is no macro garbage there, it is microplastics, so you can't see anything at the surface. So if someone shows you a picture of what looks like a dump, that is not a picture of the Pacific garbage patch, okay? Just so you know. So if we were to go out there, number one, we wouldn't see anything, and we would have to get down to, a few hundred meters probably in order to get at the actual plastics. And then number two, if we even were still to skim the surface, there's an entire biological community that we know almost nothing about that lives in the middle of these gyres that we could be killing, more or less. And so there's people who are trying to, you've heard of the Ocean Cleanup Project, come talk to me later and I will tell you all the ways why it is horrible. Because they've spent a lot of money and haven't even picked up any plastic. So, plastic, it's a problem. There was a guy who recently, he's doing, I think it's called the 7 Deeps. So he's diving the deepest part of the ocean in all of the 7 oceans. He did his Mariana Trench dive, and he saw a plastic bag, unsurprisingly. Frankly, I'm not surprised. I've seen trash on basically every dive I've ever been on or been involved with. So this was not surprising to me at all. Okay. So plastic is bad. So fundamentally we still know very little about the deep sea and the seafloor, especially the subsea floor, okay? And there's a concerted effort right now among geophysicists to actually map the entire seafloor. If you follow X Prize at all, the most recent X Prize was actually for ocean mapping. Okay, so they had a goal, they wanted whatever system was to map X amount of size at X resolution in the shortest amount of time possible. I don't remember who won, unfortunately. But that's part of Seabed 2030, which is a concerted effort to map the entire seafloor at about a 5-meter resolution by 2030. And the way we would do that would be to send out our little autonomous vehicles, and they would go around and map, and then they'd come back and give us the data. And then we'd send them out again to another place, and then they'd come back and give us more data. So, but we're really far away from that. Okay, so we're getting there. But, and just as kind of a frame of reference for that, we've been studying hydrothermal vents for 40 years. Okay, so they were discovered in 1977, which was 3 years before I was born. Okay, you can do the math there. Even though we've been working on them for 40 years, we still really don't understand some very fundamental things about them. And not just geology-wise. We have no idea how the larvae from the different critters that live there, how those things migrate to another vent. Okay, because these things are like little islands, okay, along the mid-ocean ridge. And, for them to basically the larvae would have to go maybe kilometers and kilometers and kilometers in a direction where there might be no current. So how are these things being populated? So that's like a really fundamental question that we haven't been able to answer, and we're not any closer to it now. But only by continuing to explore the ocean can we actually move towards a better understanding of how the planet has evolved through time and how human activity is affecting the deepest parts of the world's oceans, okay? Now, I don't want to be a downer, so I'm going to leave you with some cool stuff. Okay, so I have some friends, and I mentioned this earlier, they are working on what is effectively underwater Wi-Fi, okay? And so this would be, the purpose of this system would be to, there we go. The purpose of this system would be to untether the robot, okay, untether the ROV from its clump weight. So that's an additional safety issue we have. The tether can get hung up on things, it can get wrapped around things. So they put out a receiver, and they're actually transmitting the data from inside the submersible to the package that they put on the seafloor, and they're watching this inside the submersible as it goes. So their data speeds are quite fast. Okay, they used one of my data loggers as a test bed before they went to this, basically they would, they put a a sender on my unit, and then they'd lower a receiver on a line, and then query my data logger and get all of my data in 30 seconds. You know, something that would normally take me a couple of hours to download. So their speeds are great. The clarity of the water at this step is very, very good. So there's not a lot of particulate matter. Nothing is attenuating their signal. So they're still working on this. It's in progress. Okay. And then the other thing I want to leave you with is a misconception that I hear a lot. Okay, so how many people think you need to be a genius to get a PhD? It's okay, you can be honest. Like, it's okay, it's okay. I used to think this too. Okay, so a few people, okay. So, you don't have to be a genius. I'm not a genius. Like, I'm pretty smart, but I'm not like, you know, I'm not Stephen Hawking, okay? So, I like to think of all of the, you know, human knowledge in the world as a circle, okay? We're in elementary school, we get a little bit. We go to high school, we get a little bit more. And this is where you guys are right now. You're going to college. You're going to get a major. You're going to put a bump on your amount of knowledge. You're going to know more about one thing than maybe some of your peers will, okay? And so let's say, you know, say you decide to get a master's degree. You make that bump a little bit bigger, okay? And let's say then you decide, oh, I'm going to read more papers, I'm going to get a PhD. You're going to make that bump go all the way to the edge of what we know as human beings right now. And if you just push at the edge of what we know, just keep pushing, you might make a little bump, okay? So you're taking one bite out of all of the things that we don't know, okay? And that's what you're doing with a PhD. And so once you're in that bump, your perspective is completely different, right? You're like, whoa, I can go anywhere, this is amazing, I know all this, you know, I'm in this completely unknown world, I can do anything. So just keep pushing, okay? And with that, I will take questions. How many do I get, Brian?
Let's go with 5.
5 questions? All right. All right. Yes, in the back. What's the most interesting thing I've seen while I've been in a submersible? Well, I'm a little biased. I think corks are really cool. Funny enough, I've actually never dived on a hydrothermal vent system, like an active chimney venting system. So normally I would say that, but I haven't seen one in an HOV. Probably, okay, so the corks, as you can imagine, provide a small amount of habitat for critters that would live at the bottom, right? So octopus families like to live at most of the corks. And one of these octopus decided it really liked my data logger and did not want to move out of the way when I wanted to plug in to download my data. So we had to do a lot of cajoling with the manipulator arm to try to like gently brush it away, and that's also where the toilet brush comes in. Because you don't, I mean, these are, you know, big titanium manipulator arms, you don't want to like, you know, smack the octopus. So we nudge it gently out of the way with the toilet brush. So that was probably one of the coolest things that I've seen, was just that procedure of going through and trying to get this thing off of my data logger. Also, when the last dive I had, which was actually the deepest one I've had 7 dives total. This last one was over 10,000 feet. We were at a rock outcrop, that Dorado outcrop, and the area we were exploring, no one had been there before. So my geologist eyes were the first to see that rock, and that was really, really, really freaking cool. Okay. And somebody had a question in the middle. Did I answer your question from before? Whoever had the question in the middle of the talk? Okay, okay. Well, there's a good one that I'll stick in at the end. Yes? Oh, that's a good one.
How do you feel about efforts made to mine minerals and store it? Like, do you think it would be good announcement?
So, okay, so it depends how they're doing it.
Can you repeat the question?
So, sorry, the question was, mining minerals that might help with the chemistry of the ocean, is that worthwhile? And, you know, what are the pros and cons of that? What do I think about it? If it's done ethically, if it's done, and the thing about, because I know you're thinking about olivine, right? The nice thing about olivine, we don't have to get it from the beach. deep sea. We can get olivine from, there are places where the ocean crust has been pushed up on land. And so we can get olivine on land. So if we were going to do that, I'm all for it. I'm into it. But if it means that we're effectively going to have to destroy something in order to get at it, I need to see an environmental impact study first. Okay, that kind of answer your question? We can chat more about it later. Okay, Chris, in the back.
I was just kind of curious about the training that goes on for the people inside HOVs. Because while the environments are very different, I imagine the stakes are pretty similar to astronauts. Because if something major goes wrong and people on the surface can't help you, you're probably going to die.
Well, okay, so Chris is asking about the training that you go through. Now, do you mean like pilots or do you mean scientists?
Both.
Both, okay. So the Navy actually owns Alvin, okay? So you're limited to daylight dives because the Navy basically dictates what we can do. We have to do everything in triplicate, all the paperwork. It's awful. So we go in the water at 8 in the morning. We have to be back by 5 p.m. All of the pilots are Navy trained, okay? So they go through a pilot and training process. They basically learn how to put together and take apart all of the systems in the submersible by memory, and then they take a series of board exams that are supervised by the Navy, and they have to show that they're, competent in this area. And so, like, I think my boyfriend started his pit training in like 2003, and he didn't become a pilot until 2006. So it takes several years to do this, and this is continuous work at sea. Now, scientists, when we go out, we don't get all the training. We get some of the training. So we go out, immediately they put us in the sphere, and the first thing they look at is, are you going to freak out? Are you, claustrophobic? Things like that. Because they can tell right away. And then we get training on, like, if there was a fire, what do we do? We have, oxygen masks in the sphere. Basically, we put those on, we turn off all the oxygen that's ambient in the sphere so that we could put out the fire. That's really the most dangerous thing that could happen in the sphere. If for some reason the pilot were to become incapacitated or we got caught somehow, we learn how to operate the weight releases and how to drop, you can actually drop off the manipulator arms because they're quite heavy also. So there's a certain level of training that we go through, but the nice thing is about the sub is that you're at 1 atmosphere of pressure. So we don't have to worry about like decompression or anything like that because we just stay at, actually they bring us up to about like the equivalent of about 10,000 feet of altitude, just so they can keep the oxygen levels a little bit lower to prevent fire. And some people get a headache. I don't really have a problem with it. But there is a little bit of training. For the pilots, a lot more than the scientists. We just get kind of basic safety training. But the Alvin is great. It has never had, knock on wood, it has not had a major safety issue in over 5,000 dives. Okay, the only time anything bad happened to it was in the 60s where they were using a completely different launch system and it fell off. And fortunately, the people who were in it were able to get out. It was fine. It sank. It was on the bottom for a couple of years. The bologna sandwiches that they had packed for lunch were still good when they recovered it 2 years later. So that says something about maybe bologna. They don't give us bologna anymore. We get a nice peanut butter sandwich, which I usually forget to eat. Does that kind of answer your question?
Yes.
Okay, cool. We can chat more about it later too. Okay, yes.
Does the Alvin have a bathroom?
Does the Alvin have a bathroom? Thank you. That was the question I was going to inject at the end if no one asked. So, the Alvin does not have a bathroom, okay? So you're in there for 9 hours, right? Okay? So, we go in bottles, okay? For short, local phone calls are in bottles. And so, as you can imagine, it is easier for the gentlemen to do this than there is the ladies. But all the ladies get a Lady J, so like if you gotta go, it's cool. The pilots are really nice about it. Like there's blankets, you can kind of like section off your part of the sphere. They'll turn the music up so no one's listening to you. Like, no, they're very good about it because they know some people are very sensitive about it. Now, a long distance phone call. That has only happened 5 times in the history of the submersible. Okay, the submersible's been operating since the 60s. The options are few and horrible. And I will not say anyone's name to protect the guilty. But they usually involve a garbage bag, and that's all I'm going to say about it. Yeah. It
One
did
more.
happen a couple years ago, but yeah, it's pretty horrible, so, yes.
So, you said that a lot of what we think we know about convection mantle isn't actually true, but we're doing science.
Well, yeah, okay. So, do you want to know what it actually is like?
Yeah.
It's, the problem is that we don't know, okay, so the question was, I said that we don't know what the convection in the mantle actually looks like, okay? So first off, the mantle is not a liquid, okay? I want to make that expressly clear. The mantle is not like boiling water, where you can put the dye in and see the convection cells, right? The mantle is actually a solid, okay? The mantle is a viscoelastic solid, meaning that over long periods of time it flows, but over short periods of time it's a solid, okay? So that aside, convection cells in the mantle do not just kind of run perpendicular to whatever it is they have it perpendicular to. They're usually 3D. If you Google mantle convection, you should be able to find some animations of some thermal modeling that's been done. But it tends to be a lot blobbier and not these nice circular cells. Okay. It's too bad because it does look pretty in the book. It's true. It's true. Anybody else?
Last
Yes.
one.
So I live not far from the Gowanus Canal, which apparently is one of the 5 most polluted waterways in America.
Oh, really? Okay.
Yeah, and so one of the things that they're doing is they're raising oysters and planting them around. So I'm wondering how viable of an option that is, especially cleanup pollution would belong to.
Yeah, so the question is, how useful are, planting oysters or shellfish, basically to alleviate or to mitigate pollution? And that's actually very common. And from what I've read, it works pretty well. I'm not a biologist. I will preface this by, making that clear. I'm not a biologist, but from what I've read, because basically what they're doing is they filter the water and they're pulling all the bad stuff out of the water. So obviously, we probably shouldn't eat those oysters, right? Yeah. But are they cleaning the water? Yeah, they're doing a decent job of it. I mean, we can't just do that and just allow them to, kind of be responsible for filtering out all of our crud. But at the same time, it's a good way to start. So I'll take more questions at snack or whatever. You guys will find me. Thank you guys very much.